Today's background is the Blue Pool at Bermagui, which is one of the smaller towns on the south coast. And it has a really nice rock pool that was built in the 1930s when a bunch of people from the local surf club decided that they needed a second pool because there's another one further round that's sort of just a netted piece in the ocean. And they wanted a pool that they could use for training and potentially competitions. So while they were trying to get money to do this project, they started, just working on dynamiting out this nice, big, almost Olympic length swimming pool into the rocks down by the sea. And particularly, well, I'm a bit of a swimmer. If others of you are swimmers, is one of the really nice ocean pools that you can find dotted up and down the coast of New South Wales. Highly recommend visiting it. It's a good swim in summer or even in winter if you can brave the shivering run back up the stairs to the change rooms. So in this second half, I want to take the ideas that we had for classical correlation in the first half of the lecture, and I want to take them quantum. So let's come back to our characters. What we're going to do is let Alice keep her quantum coin. And in this case, it has states up and let's call them up and down rather than heads and tails. The reason for that is I want to start coming back towards the notation that we have for our quantum spin system a little bit. And imagine that she has superpositions that look like we normally see superpositions for up and down states. So up is heads, tails is down, okay? And then what we're going to do here is let Bob have a quantum coin as well. We'll give it a slightly different look so we can keep track of which coin's which. And his will behave in the same way. He'll have two basis states, an up and a down, and be able to form superpositions. And in order to distinguish the basis states for one from the basis states of the other, we're going to change the notations of the brackets as we talked about in the first half. In order to keep track of the prefactors for superpositions, what we're going to do is call Alice's alpha and Bob's beta, so Greek letters for the first letter of their name. And then they have their own vectors, they have their own superpositions. They're going to need their own operators, right? Alice is going to want to be able to measure her coin. Bob is going to want to be able to measure his coin. And so what we're going to do is keep sigma for Alice, just to keep things nice and simple, so we keep track of all our usual operators. And then for Bob, what we're going to do is choose the next letter in the alphabet. So T comes after S, so we're going to use tau, okay? That way we're going to keep track of when we have to apply spin operators later on to work out eigenvalues and eigenstates. We know who is doing the measurement, whether it's Alice or whether it's Bob. We can also have operators that act on combined states in this system, and you'll see some of them come up as we get later on. Okay, so very quickly, 3 rules that we're going to have for our combined states in our mathematical framework here. First, we're going to have an operator that works on combined states. So combined states is this idea from the first half where we take a tensor product of the individual spaces and bring them together. Okay, so now we're defining a set of operators that work in that combined space. Of course, because that operator is now working on a space that has a bigger number of dimensions, it needs to be a bigger matrix. So these matrices will be 4 by 4 for 2-spin systems, and they would be 12 by 12 for the coin and dice combination that we talked about in the first lecture. In this year's course, we don't have enough time to get into the mathematics of doing combined states. I've done it in past years. So you won't have to know how to handle these big 4 by 4 matrices, but when I give my optional lecture on quantum mechanics, I'll show a little bit of it so you've just seen it. And if you go on in this topic, you'll get used to using that. We also have vectors in this combined space, and we're going to make them so that they're orthonormal, okay? And what that means is that if they have the same labels AB, then they're parallel to each other and the inner product is equal to 1. And if they have different labels from each other, then they're orthogonal to each other and the inner product is 0, okay? And so all we're doing here to turn this into one equation here is using our Kronecker delta notation. So this first one is 0 if A is not equal to A dash, and is 1 if A is equal to A dash, and B behaves in the same way. And so this is basically just a way of writing how to generally make it's such that they're 1 if the labels match and 0 if they don't match. And you'll notice here you require both of them to match, sort of like an AND logic here, because 1 times 1 is 1, 1 times 0 is 0, and 0 times 0 is 0. Okay? And then the last thing is we have this sort of completeness requirement that comes into our combined space, which is that if we take any state in this combined space, it can be expanded in terms of the basis vectors, right? So now what we would have is, as a combined space for our 2 coins, each of our 2 coins would have their own 2 by 2 matrices and 2-dimensional complex vector space for dealing with it individually. And then the combined space here would be a 4-dimensional complex vector space with 4 by 4 matrices. And the basis vectors would be, some combination of up, up, down, down, up, down, down, up. Those are the 4 dimensions that we define. And then any vector in that state can be written as a linear combination of those basis vectors, okay? And what I'm going to start doing here is slipping into the notation that often gets used for states in the combined system. We would reserve A for, like the ket A for Alice's system. We would reserve the ket B for Bob's system. And what we're going to do is, in our combined space, often we're going to call this thing psi. Okay, same as we have for wave function. So what we would have here is prefactors connected to each of the basis states that gives us some state in that combined space. Okay, so really all we're doing is just expanding up to deal with 2 spins compared to 1 spin. Okay, so there's 2 important states, and I really just want to deal with these 2 important states today and then stop, so that in the next lecture we have them ready to go when we really get deep into aspects of entanglement. The first one is what we call a product state. And what we can do here, because we actually don't really care about the correlations between the 2. These product states are what we basically consider to be unentangled states. You could imagine basically just Alice off on her own playing with her own spin, Bob off on his own playing with his own spin, and just looking at the 2 systems together with no interaction between them. So we don't need Charlie. So let's assume that Alice and Bob have their own Qtrons, and what they can do is they can set up their own initial spin set state. And you could get them to set them both to up, but what we're going to do is get them to set both to some superposition of up and down, okay? So Alice's spin will be in some state that's some mixture of up and down for her spin, and then Bob's spin will be in some mixture of up and down for his spin. And then those 2 states will be independently normalized. So what we know here is that the prefactors alpha u and alpha d will obey a relation that looks like this. Basically, we're just saying that probability of up plus the probability of down must be equal to 1. And Bob's will do the same thing. Probability of up plus the probability of down has to be equal to 1. What we can do is write a very general state straight up here, ignoring any connections between the 2, that is called a product state. And it's called a product state because we take one and the other and we just multiply them together, right? So what we've got here is our first state here on the left, which is Alice's state, and our second state here on the right, which is Bob's state. When we multiply them together, what we're really doing is just getting 4 terms by multiplying 2 bracketed sums together. So we would get terms from the first and the first, so alpha u, beta u, up, up. Terms from the second, so alpha u, beta d, up, down, and so on all the way through this sequence, okay? And so this is just a way of taking 2 completely independent spins and putting them together into one mathematical system. One thing that you'll notice is that if we can go from the product up here to the combined state down here, we can always go back again, right? So this is multiplication, but this step back is factorization. And you'll notice that this thing at these prefactors at the front are a probability for Alice's system. These prefactors here at the right are the probability for Bob's system. And then if we combine this whole state together, we've got the probability of the combined system outcomes. And if you think about that for a few minutes, you'll realize that they are factorizable, right? The probability that we have for the combined outcome will just go back to the product of the probabilities for the 2 individual spins. So that's pointing to us already, because the probability is factorizable, that there's no correlation in here. And so this is essentially a zero entanglement state, right? They're two completely independent things. And, if Bob does a measurement on his system, he will find either it's spinning, the spin's pointing up or the spin is pointing down. And Alice's system doesn't care, right? It will do whatever it's going to do because they're two separate systems. So, Alice might measure it later. She might get it down. Bob might have got it down. It doesn't really matter. They're independent systems. We can even get rid of one of them, and we're just back to everything we've been dealing with for the first 6 lectures, which is a single spin system. Okay? So these are product states. Zero entanglement. Then what we can do is write more general states where we basically have built-in connections between the two systems, in much the same way that in the first half of the lecture we had Charlie prepare states for Alice and Bob that had some sort of correlation between the states of the systems that came down. The most general way to write this is in a form that looks like this. Our state in the combined space is basically a linear combination of all the possible options: up, 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 down, up, down, down. And this whole thing has to be normalized, right? So what we would have here is some normalization here that says the probability of up, up, plus the probability of up, down, plus the probability of down, up, plus the probability of down, down, has to be equal to 1, okay? This state is more than what can be prepared independently by Alice or Bob, right? And the something extra that's in here is something called entanglement. I'll come back to this general state in a moment. Often what you want to do to make sense of this is actually go to the maximum amount of correlation. And you remember when we did our classical experiment in the first half, that's exactly what we did. We set up the experiment so every single time the result was correlated, okay? And so not exclusively, there's more than one way to do this, but the most common and usual starting point for doing this is a thing called the singlet state. And the singlet state is a state with maximal entanglement. It's basically a state where the outcome is always correlated. And it looks a little bit like this. It is basically 1 over root 2, and the 1 over root 2 is just a normalization, right? It is a mixture of up, down, and down, up. There's no up, up, because we don't want a possibility of both of those being, of that coming out. And we don't want a down, down, because we don't want that coming out either. We're basically building the quantum mechanical equivalent of the original classical experiment, which was either an up and a down, or a down and an up. And the way to do that is basically to write a state like this, okay? Some of you at this point will be going, hang on a second, why the minus and not the plus? There's one with a plus, but we call it something else, and I'll talk about that in the next lecture, okay? So for the moment, suspend disbelief at the minus. It's not an error, it's correct. We'll look at the plus case in the next one. It's a member of a set of other maximally entangled states that always go together as a set, and the one with a minus is the one that hangs out off the side for reasons I'll talk about next time. Okay, so what I want to do here is basically show that a singlet state is not a product state, because if you remember back to the first half of the lecture, when we have a correlated system, one of the hallmarks of a correlated system is that we can't take the probability of the combined events and factorize it back into the probability of the individual events. And what we saw a few slides ago back here with the product state is that the same idea is the case if we have an entangled state. Because the state is connected to probabilities, the question really is, can we factorize that state back to its individual states for the two spins? So what I want to show is that we actually can't do that. And the way to do that is to show that a singlet state cannot possibly be written in a product state form, which is a factorizable form for the combined state. So we're going to need some paper for this. What I'm going to do is let's start by considering our product state. It's going to be alpha up, beta up, 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 plus alpha down, alpha up, beta down, plus alpha down, beta up, plus alpha down, beta down, like so. Okay, I've just got that there so we've got it for reference in a second. And then we can take our singlet state and let's write it in a form that sort of looks a bit more obviously like a product state. So the up in there would be 0. So this would be 0 up plus 1 over root 2 up down minus 1 over root 2 down up plus 0 down in here, okay? And so what we should be able to do if the singlet state was a product state is basically just compare the prefactors for each of the combined basis states with the prefactors for the combined basis states in the product state, and then be able to get something that just comes out as factorizable, okay? So let's work our way through this. What we know from the first one is that alpha up, beta up is equal to 0. The second one here is that alpha up, beta down is equal to 1 over root 2. Look at these two. Alpha down, beta up is equal to minus 1 on root 2. And the last one here, alpha down, beta down will be equal to 0. Okay, so let's think through this for a second. We'll start with the first bit here. To get that, there's two ways. One is that alpha up is equal to 0, or beta up is equal to 0, right? The only way you can get a product to be 0 is one or both of the two numbers has to be 0, okay? If alpha u is equal to 0, so let's suppose the first one, if alpha u is equal to 0, then alpha u beta d, which is equal to 1 over root 2, cannot be equal to 1 over root 2, right? Because if alpha u was 0, it would be 0 times something. 0 times something has to be 0. 0 times something cannot be 1 over root 2, okay? So we know that that's just a completely impossible possibility, right? If alpha u was 0, the prefactor for the first half of this singlet state cannot possibly be 1 over root 2. So let's consider the other option. It's got to be beta u is equal to 0, right? So if beta u is equal to 0, then alpha d beta u would have to be equal to 0, right? Alpha d could be anything, but beta u is 0 and something times 0 is 0. But of course, we know that it's equal to minus 1 over root 2. That's impossible as well, right? There's no way that something times 0 can be 1 over root 2. So that can't be true. So it's impossible for alpha u to be 0. It's impossible for beta u to be 0, which means it's impossible for the product alpha u beta u to be 0. And so it's impossible for us to write this thing as a product state, right? You can take the same logic on the opposite side. You can look at the alpha d beta d case and find that that has to work in the same way, right? So what we basically show here is that it's impossible to write the singlet state in a form that looks like the product state, which means it's impossible to write it in a form that's factorizable, which means that there must be correlations occurring in this thing. There's an alternative route to proving the same thing, which is to show that the expectation value of the spin matrices is equal to 0. And I'll either leave that one to an exercise, or if I have enough time, I will do that one in the next lecture, okay? But what we're seeing here is basically a state that cannot be factorized, so it's got correlations, and it's basically the quantum mechanical equivalent of the first classical correlation experiment that we saw Charlie do. It's basically Charlie takes a spin up and a spin down, and or he could take the opposite, whichever one, puts them into a system, into a way that Alice and Bob doesn't know what the states of the system are, passes it to them. And there we have a state that's got a correlation in it, right? We don't necessarily know whether Bob spins up and Alice's spin is down or vice versa. We know whichever way we do this, there was, when the state created, some correlation between the two, okay? What I mean here, just as one last point, by maximal entanglement is that the result is correlated every time you do the measurement. Let's think back to the first lecture. You remember that there was perfect correlation, which was the case where Charlie every single time took a Dogecoin and a penny, put it in 2 envelopes and delivered through the slots to Alice and Bob. And then we had the state where we had no correlation, where Charlie took penny and Dogecoin, put one through the slot, threw one in the bin, penny and Dogecoin, put one in the bin and put the other through the slot. States that happen in between, these more general states that you have up the top here, would be a little bit like an experiment where basically Charlie had the memory of a goldfish and he wanted to do both experiments, but he couldn't remember which experiment he was doing at any particular time. So he might start out by doing penny and Dogecoin into the 2 and through the door, through. Then he might for a while start doing the 2 envelopes experiment, and then he might just, be really goldfish and just completely, I'll do various versions of the 2. Sometimes he's doing the 2 envelopes, sometimes he's doing the 4 envelopes, completely alternating through. Then you would see some mix of correlations in there, right? I'll let you do this for an exercise yourself. Set that up as an experiment, work out what the results would be, go back and look at the statistical correlation chi, and what you'll find is that you get a number that's somewhere between 0 and -1 when you do that, right? And that's what we would call a partially correlated state. You have an equivalent thing in quantum mechanics, which is a partially entangled state. And so the idea there is it's not a product state, which has no entanglement. It's not a maximally entangled state like the Singlet State or the other maximally entangled states we'll see in the next lecture. It's somewhere in between. It's got a little bit and not a lot. And you get those states turning up when you do quantum information as well, in much the same way that you have them in classical correlation. Okay, so this is the point where I'll stop in this lecture. I'll give you a little while. It's a good point to give you a little while to think about the parallels between, classical correlation and quantum correlation, so that when we come back for the next lecture and we start looking at some of the, I guess, what naively, when you first look at the subject, are considered to be some of the weird aspects of entanglement, I can sort of demystify that a little bit and just show you that there's nothing really magical going on there. It's just correlation as you'd see it in the normal world, taken into a quantum mechanical system in some sensible way. And of course, it has to be like that, right? If we think forward from now, we're starting to build technologies on the basis of this idea of entanglement. And if we're completely hung up in sort of woohoo madness mysticism, we're not going to get very far, right? We have to put this on a firm foundation. And it is a firm foundation. It seems strange when you first see it, but the reality is it's not actually very strange at all once you get used to it. I'll finish there and see you next time.